Hi, everybody. Thanks for coming to the MagNetZ. Today, I'm really happy to have Joe Stoner from Oregon State University presenting the talk on Paleomagnetic record of Fish Lake, Harney County, Oregon Revisited, Constraining Uncertainties in Paleo-Geomagnetic archives. So please, Joe, share your screen. Thank you very much.
Okay. All right. Welcome, everybody. Always tried to avoid giving Zoom talks as much as possible now that we don't always have to. But we'll see how we do. Okay. So this is a blast from the past in a couple different ways. And I'd like to thank all my co-authors on this, Mark Abbott, Brendan Riley, Matt Finkenbinder, Rob Hatfield, Leah Ziegler, Dave Coneydyke, Aubrey Hilbin, and Bernie Hausen, who've helped in a large variety of different ways on this project over the last, more than 10 years. A few things have gotten in the way with COVID and the fire we had in the lab that requires us to move labs, and a few other things that have slowed things down, but I'm hopeful that we'll soon have this out there. Okay. Figure out there we go. Okay. So we're going to build on the really spectacular record from Fish Lake, Harney County, Oregon, that was originally published in the 1980s by Ken Verosub and others in a series of papers that was considered to be the sort of second generation of paleomagnetic secular variation studies, and this is one of them in that it used multiple cores to create a composite record. It had a large number of radiocarbon dates, and it's well been often considered the type record for the Western U.S. The beauty of the Fish Lake record is it had what was thought to be a magnetite, primarily held magnetization. It had a large number of radiocarbon dates. There's a tephrostratigraphy that helped match with other lakes and overlapping records within the lake. It was a really sharp and apparently high quality paleomagnetic record. It's often been considered the type record for PSV in the Western US. And it's really been comparable to many other archives and records, whether they're archeomagnetic or other lake sediment or lavas and speleothems. And it's often used in most most really sediment included spherical harmonic reconstructions of the Holocene. This was originally cored in the 70s as part of the Steens Mountain Prehistory Project that Pete Mehringer and colleagues really developed to try to understand the history of the Great Basin in the South and that area and how that impacted human evolution at that time. Okay. All right. So why should Fish Lake be replicated? It's a great record, but it did have a few unusual features. Inclinations were shallower than expected. Comparisons showed that the PSV was a bit older than expected. Are there other important unknowns? So, we figured that modern approaches would allow us to examine the sedimentary record, the magnetic properties, the magnetizations. All of those are related things. And really, how continuous are they? How variable are they down stratigraphic section? No records are completely continuous without variability. How does that impact the recording of the geomagnetic field? And, chronology has been brought up as one of the questions. And, is the age of the magnetization and the age of the sediment the same? Or are there variations that need to be explored? And really, replication is often one of our best tests of paleomagnetic reliability. Okay, so we're just gonna, in this talk, kind of go over three main parts. We're gonna look at the replication. a bit of an insightful exercise, just doing something again using slightly different methods and new approaches has really been beneficial and eye-opening in many ways. We'll look at some of the lithology and some of the impacts that that might have. And then we'll look at chronology, which is really our currency of comparison. It's how we compare one record to another and what that is beginning to tell us. It's not a done deal in this story. It's like many situations, it's really just opening the book and beginning to examine what's going on. Most of the paleogeomagnetic implications will come out hopefully later after we build on what's reliable, but that'll be another story. Okay, so Fish Lake, Harney County, Oregon, is located in the southeast corner of the great state of Oregon and the Pacific Northwest region of the United States. And here's a map of Oregon on the left showing where Fish Lake is located on Steens Mountain. And from a geomagnetic perspective, I always like this particular time average reconstruction from Dave Gubbins that shows the flux lobes as really stationary components of the historical geomagnetic field and where Fish Lake is located relative to the North American flux lobe. And if we think about things a little more dynamic, you know, if we look at declination historically over Fish Lake, we see that changes occur at the same time, really, as the North Magnetic Pole is taken off and moving over towards Siberia. That's happened over the 20th century. So there is some co-occurrence of variability in these locations, and therefore the paleo record might provide some insights. Okay, so Fish Lake, what makes it good? Well, it was cored. It collected. It's a small lake basin on the Steens Mountain, which is a large pile of basalt, Steens Mountain basalt, which is the oldest sort of member of the Columbia River flood basalt sequence. So it's a Miocene flood basalt, and it's a small glacial lake. Steens Mountain is known for these spectacular glacial valleys that have formed, and this lake is a small one at the head of the Fish Lake Valley. It's a moraine dammed lake. It's the only moraine dammed lake on the Steens Mountain. There are other kettle lakes that can be seen in the distance up above, and it's a small lake. It's only almost 9 meters deep. Not very large. Its elevation is 7,369 feet for us US folks, or 2,246 meters for the rest of the world. And its latitude's about 42 north, longitude's minus 118. And we took a core just offset from the deepest location in the lake. Okay, so in 2013, and I'm going to call this Fish HO 13, though my dyslexia sometimes gets in the way of me and sometimes it's OH, but I'll try to fix that where I could or saw it this morning. But in 2013, we went out and cored this lake using a Uvatech piston coring system with 2-meter long core barrels and a percussion driver on a wooden platform on a cataract with an aluminum frame. We also collected some surface cores in the lake, and we deployed a field magnetic susceptibility system. And you can see Brendan and Aubrey and Rob Hatfield there monitoring this field susceptibility system that used solar panels to power it and allowed us to really see what we cored after coring in the day and make decisions for the next day's coring routine, which allowed us to get a really continuous sequence as depicted in this figure here in the lower right. Okay. All right, so once it was cored, the cores were brought back to the OSU Marine and Geology Repository. where they were CT scanned initially, and Brendan Riley built some software to facilitate the analysis of this and use of extracting CT number from the data and image quality and building images in said CT, as well as the cores were then subsequently split, photographed, described. Working halves were subsampled for density, loss on ignition, radiocarbon that was measured at Pittsburgh, grain size and U channel at OSU, and the hysteresis loops were done up in Western Washington with Bernie Hausen at the Pacific Northwest Paleomag Lab. To look at what some of the cores look like, these are photographs above, high resolution line scan photographs above, and CT scans below. The CT scans in both of these show a laminated sequence throughout that has tephra layers occasionally that can be depicted, and these are known from the original study and a really prominent part of that record. Here are two in the surface core. Also note the inclined laminations, which we will subsequently correct for the paleomagnetic record. So having both the photographs and the CT scans are super valuable. We also got to see how much gas is trapped in these from the CT scans, which we weren't aware of, that are in these voids here, and happy to talk more about that and CT scanning in general and how really an amazing new approach it is. You can really see in this deeper section how well laminated these sections are, and it is laminated throughout. And then below we have the Mazama climatic tephra from the eruption that created Crater Lake. And that was about 7,600 years ago, and it's preserved here, as well as the Lau Rocks eruption that's just, that happened just before that. Okay. All right, so different PMAG teams worked on this. Primarily Leah Schwang was going to do a little bit on this, and Rob, he's twice in these two different pictures of earlier groups, and Brendan Riley at the OSU PMAG lab. We took U-channel samples. This is not Fish Lake, unfortunately, but another laminated lake sediment sequence, and this is our old lab configuration prior to the fire. We now are in a new setup and have a new RFI shielded system that's giving us really spectacular results, but I'm showing this as these were measured in our old configuration. The response function as mapped out by ERDA and June, and yeah, we measure this every centimeter. We study the NRMs, ARMs, and IRMs with somewhere between 14 and 17 AFD magnetization steps, usually at 5 millitesla intervals. We also measured magnetic susceptibility on the U channels using a Bardington 36 millimeter loop with our in-house built tracking system that we deploy for all our measurements. Oh, I'm not going to leave out Sammy and Deepa and Sam, who are part of the PMAG lab today, and they're doing wonderful results. And Sammy is going to be adding value to some of these results at AGU and further on in the future. Okay, so the recovered sequence looks like this. It's really, this is a great depiction of it. It shows the CT scans and then HU numbers on log scale and magnetic susceptibility to the right of that for each drive. And what a composite record would look like here in the center with both the HU number, here the CT number, the HU units on that, and magnetic susceptibility log scale on the right. So there is some lithologic variability in these records. As you can see, the color is denoting the different drives that are based in this. We use this initial splice sequence kind of following IODP alignment, and then we correlated every core into every drive into the splice sequence to come up with an optimized composite depth so that we can map all of the sections into the splice and make stacks based on that. So everything is mapped into this splice sequence. 6 visual tephra layers. I wanted to bring this out. The Fort Mehringer and Mehringer paper that came out in 2016 published all the radiocarbon dates that were associated with the Fish Lake original study, as well as brought out the tephra layers and what's known about them. There's 6 visual tephra layers that were the focus of study and allowed them to correlate from lake to lake. And they used it in all of them to sort of really come up with a stratigraphy and help chronology. And this is a really nice and very useful paper for this study. So these are important stratigraphic ties. Okay, so I've tried to show the tephra layers where possible on most of the record, though I may have left them out in some of the later things, but this shows them. And then this is all of the U-channel data, susceptibility, MAD values from left to right. And then we look at the inclination of all the drives here. So we have the MADs of all the drives and the inclination of all the drives. And we took in that into account. We corrected for offset, as I previously showed, incline bedding was corrected for this upper one in the second inclination column. And then we made a stack based on that. And we propagated the uncertainty using the MAD value to alpha 95 confidence interval from Kokolov and Hulot. And then we propagated that through in our stack using the Donadini and then the Seti and Nielsen method to develop an uncertainty for our stacked inclination. Declination, a little more challenging. Drives all start out with a mean of 0, which is shown on the left for declination. We then correct a few for linear possible rotations during coring. You can see that in the top one here, and then this lower section here. These two were corrected for a linear trend that allowed us to have this sequence. Whoa, sorry about that. Sequence here. And then we basically pruned off these parts that didn't match in the lower part of a drive. Tops and bottoms of drives can sometimes be problematic, and it was the lower ones that often show some offsets that didn't match with the other overlapping results. And this gave us this pruned declination record that we then used for the stacking approach. And it followed similarly with what we did for inclination using the Kokolov and Hulot sort of MAD to alpha 95s, followed by Donadini and Seti's and Nielsen's approach to help further constrain the chronology of the stacked records. And I should say that the uncertainty takes into the account the number of cores in the stack, not the number of data in the smoothing that we use. Okay. So if we look at that further, which is the primary part of the new record, our stacked records are here. We have some of the statistics below, just to point out, GAD is about 61.5 degrees, and the 400-year average inclination is 67.7 plus or minus 9, and declination, well, it's changed quite a lot in that time, 12.1 plus or minus almost 7 degrees. Inclinations are steeper than average, and some of the steepest of any time in our record. And our means are close to this. Our mean is 59.6, so almost GAD. Median's close. The range varies around that from 47 to 71. Our declination range, of course, this has rotation and assumptions in there. We have a mean of 1.2, median of 1.3. The range is 23.3 to 21. And you can see in our reconstruction, the top shows this sort of anomalous feature that's characteristic of the last few hundred years, these easterly declinations. Okay. So we got new records, and now we want to compare with the old records to see where we are. We took let's see what we did. We took the original Fish Lake record, all the discrete samples, which are great. We then smoothed those using an 8 centimeter Gaussian smooth. And we look at the inclinations here. The main point is that the mean is quite a bit shallower than what we found. It's 51.2. And the declination is whatever the declination is, but we have a very nice comparable record. We then want to compare the two, and because they record at different times, we use the tephra layers in both of them to align the records, which is shown here as the tephra correlation. And then for the bottom part below tephra, we used a few PSV features following along a line of really constant relative sedimentation rates to align these records to each other. Kind of looks like something like this. This is the original Fish Lake with the smoothing on there and its depth that's then converted based on these tie points to this record here. And here's our new Fish Lake. So we put everything on the new Fish Lake depth. We then corrected the mean and placed them on a common mean for comparison. And what we end up with is this. These are the original Fish Lake statistics. So the mean's quite a bit shallower. So we added 9 degrees to inclination for that. We subtracted 9 degrees from declination. And when we do that, we get something like this, which overall really I think is astounding that the similarities are so good and so comparable, and really shows that the long period PSV variations are super well captured at this site. I think one point worth making is that the inclination shallowing is not an intrinsic feature of the Fish Lake sediments. Some sort of artifact of the original study. I don't know where it came from, but it's not part of those sediments. They resolve an inclination that's really very close to GAD. So I think that is a nice change. There are a few other features that came out that were slightly offset. And this is the residuals after you do this mean correction. And you see that the top shows some offset, which is not that surprising given the difficulty in coring core tops. The bottom is surprising, not very surprising, considering it's glacial till at the bottom, so that they really hit that. We didn't get into it in their coring, and that could have caused some of the offsets. And then there's this interval here between tephra 4 and tephra 5, where there are large declination differences, some slight inclination differences, but primary declination differences that I'm not sure, but coring through tephras can be problematic, and tephra 4 is proximal, and part 2 here, lithologic variations. We didn't know that in the original record. Hopefully my internet stays stable. Hard to know. Just gives me that sign, but the lithologic variability is not constant. There are what we came up with 3 different lithologic units based on grain size here. This is the silt. Mostly it's silt with some clay. Mostly it shows a lot of variability. Some intervals don't. Some intervals show a trend. As well as the loss on ignition is really high. It's a much more organic rich interval prior to the Mazama tephra. I'm just going to jump into this because time anyways. And then if we look at the magnetizations on those lithologic interpretations of 4 lithologic units, we see that the magnetizations themselves shown both in linear and log for NRMs, ARMs, linear and log, and IRMs, linear and log. Oops, sorry, this data here, IRMs, we sometimes have problems with U-channel samples when values increase too rapidly. It can be difficult to measure with our present systems, and that's what this is. So the only really good, fully good data was demagnetized by 65 millitesla before we have our IRM data that was good. But the ARMs and the NRMs all look really good, but they do show variations that generally respond somewhat to lithologic variations, though you might interpret, if you were to make interpretations based on magnetics, you might interpret a little different, like this lithologic unit might move up here a little bit. So there is some lithologic variability that we should think about as we think about the Paleomag record and what it means for Paleo-Geomagnetic interpretations. Okay, so rock magnetic, just to throw in here, that data, this is really just the beginning. There's a lot more analysis, but some hysteresis data show that there are some downcore trends in the data sets. We don't quite understand it. It might suggest that there's some small bit of diagenesis that impacted this record. In this organic, more organic rich interval, we see what would be interpreted as coarser magnetic grain size if it was a magnetite assemblage in this interval here. Subtle differences that are there. It's also showing up in the U-channel ratios as well. KRMK picks all of this up as well as the hysteresis data quite well. So there's a lot of interesting data here. If we just throw on the uncertainties associated with our stacked data, we can see that these lithologic variations have some impact on the uncertainty of the Paleomag record. And this is something we're trying to quantify a bit and understand better of how this impacts the record and what these variations are associated with lithology and what's really a relatively simple system. Okay, so move on, keep timing going. Our stacking approach allowed us to put things on common depth, allowed us to compare the radiocarbon dates. And the key point here is that the radiocarbon dates, even though the initial ones were collected through bulk dates, and those are the black squares here, or the blue open squares, compared to the black macrofossil, sort of more state-of-the-art approach regionally, they give us the same answer all the way back to about 8,500 years radiocarbon or 9,500 years calendar. Approximately, we get a very similar answer from dating. So the chronology of the original Fish Lake paper was not a problem whatsoever. Even though there have been offsets observed between lava data and lake data, it's not a chronological issue. Okay, so we have just taken this initial chronology based on the Fish 13 calibrated radiocarbon dates only. We can play a lot of games with the multiple dates later, but using this one, using a simple clams-based chronology tied to lead-210 cesium at the top, this shows where the tephra layers are. Nicely, this well predicts the age of the Mazama tephra. Well, right within the uncertainties, we get an age of 7,600, which is right in the middle of the age uncertainty, best age for that particular tephra event. So, and you see it here, it does impact the Paleomag record a little bit. You know, if we convert things into, and the beauty of PowerPoint, we can rotate these things so we can convert this from depth into age here. We can use that to convert and put our PSV record on age. We get something like this. You can see that there is a change in slope, which is telling us about a change in accumulation rate. And this is where both things agree down to about this level here. So that change in slope appears to be real. And you start to see it in the uncertainties become a bit larger associated with our directions. Okay, so comparisons. We have a chronology. We can make comparisons. There's a lot of different ways you can do this. Believe me, I've kind of run many different gamuts and still trying to come to a full conclusion on this. But if we compare to this is the archeomagnetic model that comes out of Nielsen's 2022 paper. I've compared with other archeomagnetic results, and things are fairly similar. What you see is the record's very similar in the top, but things are offset in age as the comparison is not should be expected. Hagstrum and Champion data suggest that should be the case from the lava records, and here's all of their data put into that. It shows, but things get a little different down below. The uncertainties blow up down here, and the records start to deviate somewhat. Some parts are good, some parts are a little bit of deviation. Not sure exactly why, but it's interesting. This is, oops, I forgot to move those. This is, yeah, oops. I guess I moved these things around a little bit, the plots, but this is just using the Hagstrom Western US lava data that's independently dated. You get a bit of a different story, but it still shows where you have these dates. Well, this will work. Where we have these dates, not dates, but where you have the lavas that are independently dated, supporting the archeomagnetic results, you get good data. It starts blowing up where you don't really have the data to help, and the agreement becomes different. So I wanted to point out that these lower dated intervals are really spot on with our reconstructions. This is Mazama tephra, the lava associated with the Crater Lake eruption there, and it's spot on with what we're getting. But some of these other ones show clear chronological offset. It's not the fish chronology. It's got to be related to something else, and that brings in the idea of PDRM and lock-in. So we've started to explore that a little bit, and I'm just going to finish off with some of that, where we looked at lock-in different intervals, 5 centimeter intervals, to see how it affects the record. And as you can see, you know, it can have some pretty large effects, especially when sedimentation rates are lower in the lower part of the record. This is a really large uncertainty that's likely affecting the Paleomag record in some notable ways. When we compare this with the archeomagnetic data reconstruction, I've gotten rid of the uncertainty just to make it comparable and overlaid these. You can see that really at the upper part, a large, about 25 centimeter lock-in depth is needed to get the best fit in this record. And some of it we don't quite do. So maybe there are abrupt changes that aren't picked out. I have other versions of this with the tephra layers put in because I think they also impact the PDRM process, but I wasn't able to get this fully in. There are also offsets you see where you don't have, you know, lava flows really supporting, you know, regional archeomagnetic or lava data supporting the records. And here you start getting offsets in the record, and Fish Lake is probably a better representation of that. And how we go forward with PDRM is really one of the next steps. This is the Hagstrom and Blendman compilation. It matches up pretty well. You can see with a fairly large lock-in, though a bit different. I'm not sure. This feature is not supported in our record, so there are some things that need to be looked at further. Okay, being that we only have so long, we're going to end it here, but I just want to go through some conclusions. Revisiting old sites can add substantial value by bringing in new observations with different updated methods. A robust new directional stack with well-constrained uncertainties for Fish Lake, Harney County, Oregon has been developed. Inclination shallowing, it's approximately 10 degrees observed in the initial Fish Lake study, is not an intrinsic feature of the Fish Lake sediments, but an artifact of presently unknown origin. We don't replicate that at all. When corrected for the overall replication, how outside really of the long period variations are very other than a few intervals, are really well supported between the records. The chronology of the original fish lake is well supported down to about 8,500 years. Radiocarbon approximately 95 calendar years. Discrepancies below need to be explored further, and we're working on that. Similarity of directional record with the archeomagnetic models and regional lava and archeomagnetic data support the geomagnetic origin of the directional signal at Fish Lake. Agreement that archeomagnetic models is best when they are locally supported by regional data. Improved correlations are found using a lock-in assumption of approximately 25 centimeters. Considering these are laminated sediments, that is really an interesting constraint. And we need to work on that in more detail. Changes in sediment accumulation rate greatly vary the impact that this uncertainty has on the record. If you combined both the lock-in uncertainty and the directional uncertainty in the lower part, it really does blow up. Haven't shown that. And lithology is not constant, isn't in any sequence, and variability influences the magnetic properties and the sediment magnetization, the quality of the directional record. But for about the last 8,000 years, it's constant enough to give us a really fantastic record. So that's it. And I'll stop sharing and take questions.
Thank you very much, Joe. A big round of applause. There is now time for questions. If anybody should have some, you can also type it in the chat. I guess you covered lots of data, lots of questions. You try and answer yourself, basically. Oh, Josh has a question. Can you speculate on the cause of the inclination shallowy in the earlier study?
You know, I mean, I thought it might have been the coring. It's something intrinsic throughout the data. It's the mean. I don't know, you know. You'd have to measure, go back to the old magnetometer and look at results from that and other studies. Hard to know. It is surprising.
Thanks. Any other question? People will have questions when we go off the recording.
Oh, I'm sure there'll be later ones, yeah.
Okay, I see really no questions. So thanks again, Joe. And yeah, thanks for your great talk. And I share one last slide just to remind people that these talks and the previous ones are going to be available in our YouTube channel. And there are lots of presentations that can be viewed. And we lasted about 4 years, so we'll try to keep going, even if we're a bit tired about online presentations. So thanks everybody for coming.